Welcome to Podcast 6, where we're going to turn our attention away from weak acids for a little bit and over to some weak bases and looking at the weak base equilibria constants. We brought up what it looks like very quickly earlier on, but we're going to go a little bit more in depth here in this podcast. So just like for our weak acids, where we had those acids that had an ionizable hydrogen out in front, or it could have been a cation, here our weak bases can be either molecules, and our main one that we're going to focus on is ammonia. Other amines, which are things that have nitrogens and hydrogens in them together, but ammonia is the one we're going to focus on probably almost exclusively as our molecule. And anions, all right? And again, we're going to learn specifically which anions like to become weak bases. Those are the anions that come from weak acids. All right, so if we know which acids are weak, then we know that the anion part of that can be a weak base as well. So if we have the weak base equilibria constant, right? We have, my example at the top is ammonia. Ammonia reacts with water to form the ammonium cation. So notice that ammonia, this is a good point to point this out, ammonia and ammonium, they are conjugates of each other. We're going to bring that up as we go along throughout this chapter. So just remember that they're conjugates of each other. In this case, the ammonia is the weak base. The ammonium is the conjugate acid of that weak base. All right, well, our equilibria constant Kb, since we're starting with a weak base, is, all right, products divided by reactants. And again, water's left out because it's a liquid. And then down at the bottom, that's our generic form. In case we have a generic one, it is going to be Hb times OH divided by B minus. And again, kind of like with this, again, our OH and our HB are usually 1-to-1. So sometimes we might see this as OH concentration squared divided by our base concentration. Right? They basically mean the same thing. There also happens to be a relationship between the Ka of something and the Kb of something if they're conjugates of each other. And remember, when we had conjugates there, my example was ammonia and the ammonium. They are conjugates of each other. And so what I could do is I could write out here a weak acid reaction, right? This is a weak acid reaction where I've got my Hb in equilibria with H plus B minus. And I have a weak base version on the bottom one. And so remember, if I couple reactions together, right, it says that these add to. When I couple reactions together, anything that's a product and a reactant, we can cancel out. And so those things are going to get canceled out, and we're going to be left with here water as our reactant in equilibria with H plus OH. Well, that happens to be Kw. And so remember, when we add reactions together, we take the product of their equilibria constants. And so the top equilibria constant was Ka. We're going to multiply that by Kb. So not only does Kw equal H plus times OH, Kw also equals Ka times Kb. And another way of saying that is in the logarithm form is that the pKa plus the pKb is equal to pKw. Well, the negative log of 1 times 10 to the minus 14th is 14. Well, if we look at acid-base strengths, and so these are of conjugates of each other. So again, think about ammonia and ammonium. If the Ka and Kb are inversely related to each other, right? Ka times Kb is equal to Kw. Kw is a constant, so if Ka is big, Kb has to be small, and vice versa. right? So the bigger the Ka, the smaller the Kb, and vice versa of that. And so there's some other things about, strong acids or stronger proton donors. Don't memorize all of this stuff. Okay, just remember that, right, we have strong acids. They're really good at being proton donors. We have strong bases. They're really good at being proton acceptors, right? And then we have, weak acids, which are okay at that. Weak bases are okay at that. And then we have these conjugates, and they are pretty darn weak overall. But don't memorize all these things. Just understand that there's kind of like a pecking order to them. But you could find out when you're talking about the weak acids and weak bases, you can find out how strong or weak they are by looking at the relative sizes of their Kas and Kbs. All right, let's work sample problem 18-7, where we're going to determine OH, POH, and pH. All right, so 3 out of the 4 of a 0.84 molar aqueous solution of sodium sulfate, assuming less than 5% ionization. Or sorry, sodium sulfite, not sodium sulfate. All right, so notice that the sodiums are going to be spectator ions. So they're going to disappear from our reaction, and we're going to be left with, right, our sulfites plus water, and the sulfites are going to act as a weak base, and they're going to make a conjugate acid and OH. All right, so what I'm going to do is I had to look up the Kb for SO3 2- because it wasn't given to me in the problem, and I need it to work this problem. And it happens to be 1.7 times 10 to the minus 7th. And so I know that Kb is equal to HSO3 minus times OH divided by SO3 2-. So I know that that's going to be 1.7 times 10 to the minus 7th is equal to, all right, and this is going to be x squared on top. Once we get doing enough of these, I'm not going to write out the whole ice tables. We know that that's going to be x and x divided by our SO3, which was given to us as 0.84. That would be minus x, but it says it's less than 5%, so I'm not going to include that in our problem. And so our x is going to be equal to 3.78 times 10 to the minus 4th. And remember that that is also our OH concentration. So we've got our OH concentration. And so now we can find the POH of that by doing the negative log of 3.78 times 10 to the minus 4th, which is 3.42. And then finally, the pH is 14 minus 3.42, which happens to be 10.58. So we got all 3 of our pieces of information there. All right, another podcast is in the books. So our next one is just going to be a very in-depth sample problem. And so it's going to take us quite a while to get through that one. So I set it aside as its own podcast, but make sure to watch it as it has a lot of little parts to it that I think are going to be helpful as you work through problems, not only in the homework, but also on exams.